Alright, so let's talk about Noetherian rings. Wait, why is Noetherian not capitalized? Do you capitalize? I feel like you're supposed to capitalize Noetherian, but whatever. Um, so we want to prove that these are equivalent conditions um, for a ring. So let's do one direction. So suppose a commutative ring A with one. Obviously, we're not talking about ergs. I love that name. Suppose A. I think we're going to have FG because here. These are both conditions, so we're supposing A has this condition, which we will call F, which we will denote by FG. So every ideal of A is finitely generated. And we want to prove ACC. So I can't draw these like here. Actually, sure, let's try it. Suppose A1 contained in square-ish A2 contained in blah 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 is an ascending chain of ideals in A. Then, let's see here. If we define A as a union from I equals 1 to infinity of AI, then this is an ideal. It's not hard to check that ideals, the collection of ideals of a ring is closed under arbitrary unions. Okay, so by FG, this ideal A is equal to A1 through A. The idea is generated by A1 through AK for some A1 through AK where the AIs are in A. Right, because it's finitely generated. So for this to hold, there must be some index such that A1 through AK are all contained in AN. Because otherwise this right, if one of these AIs is not contained in any AN, then that can't be an element of the ideal, which is just a union. And of course, the fact that we can, the fact that knowing this for every single particular generator applies to the fact that you have all of the generators in one particular ideal comes from the fact that we get it comes from the fact that this is an ascending chain. And so if you have like A1 through AN generators and they're in some like AI, then those generators will also be an AI plus 1. And so that's how we can guarantee that there is some index that will contain all of these. And then, for all n greater than or equal to n, let's make that readable. We have this ideal must be equal to A. Because once you have all the generators, you're equal to A, and then and by inclusion, everything else has to be A. And so hence, A has the ascending chain condition. Conversely, I don't know if conversely is the right word to use here because we're not. Yeah, it might be. Oh well, you know what I mean. Conversely, suppose that A has the ascending chain condition. let A be any ideal. I have to scroll down. Obviously, ideal of A. And we're going to choose some A1 in A. Let's see here. So then, what are we going to do? So choose some A1 and A. I'm actually kind of on the spot here trying to think. Because the way I have this argument written down, it's kind of strange, I guess. Like I feel like there's things that I could improve to make it more neater, even though the ideas of the proof are the right ideas. So choose some in A and let A1 be the ideal generated by A. Let's see here. If this A1 happens to be the desired ideal A, then we're also going to let AN just be A for n greater than or equal to 2. See here. And so if A1 is not equal to the ideal if A1 is not equal to A, rather, then choose some A2 in this ideal set minus A1, and define A2 brute to be equal to the ideal generated by A1 and A2. And we're going to continue this process. Inductively. So we're going to prove this. So continue this process inductively. So if AN is so if AN is not equal to A, well, if AN equals A, yeah, so if we get to some N, so what does this process look like at the nth step? So at the nth step, if AN equals A, then set AJ equal to A for all j greater than or equal to n plus 1. And if AN is not equal to A, then choose some element AN plus 1 in our ideal set minus AN, and define AN plus 1 to be the ideal generated by A1 through AN. No. Through AN plus 1. And so then you just start back and you do the process at the n plus 1 step, and you just keep going. Let's see here. Okay, and we're basically done. Because, and I think there's a better way to write what I'm about to write, but let me just write it. If there does not exist some n, natural number, such that we're using A's here. A is equal to AN, which is A1 through AN. Then that means that A1 contains is this going the wrong way? No, that's the right way. A1 subset of A2 subset of blah, blah, blah. Contradicts the ascending chain condition. Because basically, if at every step we can always add on another element, then this ideal is not going to be finitely generated. Because if it were finitely generated, then if it were finitely generated, then we would be able to stop this process. Okay, so let's see here. This A1 subset of A2, this contradicts ascending chain condition because this will give us a proper ascending chain which does not stabilize, i.e. it does not become the same thing at some point. See here. So there does indeed exist an N and N such that A equals AN equals A1 through AN. And so, see here, so A is finitely generated. This holds for any ideal A, and hence the ring A has FG. And so there we go. This establishes the reverse direction. And so we now know that being Noetherian, which by definition means having this ascending chain condition, is equivalent to the fact that every ideal is finitely generated. And there is actually another here. I want to look this up real quick because there is another equivalent condition which I should have memorized. I think it's something like something about maximal ideals, like a unique maximal ideal, something or other. See here. Okay, so let's see here, Noetherian. Yeah. So equivalent conditions for rings are: you have Noetherianity, i.e. with the ascending chain condition. You have that an equivalent condition to that is that every ideal is finitely generated, and then another equivalent condition is that every non-empty collection of ideals has a maximal element, and this is of course maximal under containment. And that sort of makes sense why that should be sort of the same thing as ascending chain condition, because you can view this ascending chain as a collection of the ideals of a ring, and this is totally ordered under inclusion. And so to say that it has a maximal element means that there is some ideal which contains every ideal in this chain. Right, but the fact that maximal element is actually obtained in the sequence. So if it were the case that you had an ascending chain which never terminated, then you have this collection of ideals, and you have a maximal element by taking the union of all of the ideals, but this union is never is not necessarily going to be obtained. Well, actually, if this chain is a strict chain, like each inclusion is a strict inclusion, then you will not obtain the maximal element, because every single ring in this, every single ideal in this chain will be missing some elements of the union of all of the ideals. And of course, the union of all of the ideals is the maximal element. And so, and again, here you have to be careful, because by maximal element, we mean it's an element of the collection of ideals. Not to be confused with an upper bound, which is something which contains all of these ideals. And of course, we do have an upper bound. You just take the union and you get the upper bound. But this union, but the upper bound does not need to be part of the subset that you're considering. And in general, if you have a proper ascending chain, then the upper bound will not be contained in the proper ascending chain itself. So you can sort of convince so that's sort of a really intuitive argument as to why you should expect that being Noetherian and having the ascending chain condition should be similar to the equivalent condition that every non-empty collection of ideals has a maximal element. But of course, if you really want to know it for sure, you can prove it, or you can read it. Most textbooks, like if a textbook actually talks about Noetherian rings, this is probably one of the first things they prove. But yeah, anyways, that equivalent condition is not necessary for this problem. Actually, you don't even need to know what a Noetherian ring is to do this problem, because it tells you. It tells you that Noetherian means ascending chain condition, and equivalently it means all ideals are finitely generated, and you have to prove those. So you never have to have seen a Noetherian ring in order to do this problem, which is kind of like, I don't know, interesting. It could be like, if they really wanted to test your knowledge on Noetherian rings, they should say, like, prove a ring is Noetherian if and only if every ideal is finitely generated. And then you have to actually know, okay, what is a Noetherian ring? What is the ascending chain condition? But anyways, I've been rambling a lot. These are all good things to know if you want to really understand Noetherian rings, but you don't need to know them to do this problem. All you need to do this problem is to do what I just did. And so here is our solution, and we are done.